So hello everyone. So then I would like to start our AIP Open Seminar. So before we start the seminar, so I want to announce some important notices about this seminar. So first, the reproduction is prohibited. Okay, the reproducing all or any part of the contents is prohibited without the author's permissions. And this seminar will be recorded and the video will be available on the Weekend AIP website later. And finally, if you have any questions or comments, please scroll to the bottom of the page and click the Q&A tab. So please use the Q&A tab for question and comments. And you can put questions or comments in the box. Okay. So then let's start the seminar. So, okay, so let's start the seminar. So, hello, so my name is Taiji Suzuki. I'm the team leader of Deep Learning Theory team, the AIP Weekend. I'm also affiliated to the University of Tokyo. And so thank you for coming. So it is my great pleasure that we have so many audiences. So I'm happy to give our presentation to you, okay? So first, I will give a presentation about the overview of recent advances of our deep learning researches. Okay, so the deep learning theories. So we have seen huge success of deep learning in wide range of applications. So the deep learning has shown best performances in many tasks. So that is amazing. But on the other hand, we haven't understood why the deep learning works so well in much details. Okay, so we need more theories to understand what's going on inside the deep learning. So we are developing a theories to reveal the essence of deep learning in our team. Okay, so this is a general purpose of our team. So we are developing a theory that can explain why deep learning works so well. And yeah, so based on this deep learning theories, so we also want to reveal what is essential to achieve a better method. So we are not restricting ourselves to deep learning, but also we want to find what is the essential thing to characterize a good learning system. Okay, and through these theories, finally, we want to develop a theory that is potentially helpful to develop a new method that could outperform deep learning. Okay, so we want to find a method that can be beyond the deep learning. Okay. So unfortunately, we are not at this stage, but through the lens of deep learning theories, we want to reach this level of theories. Okay, so this is our general purpose. This is the general purpose of our team. So for this purpose, there are some members in our team. Unfortunately, our team is not so large, so our team is very small, but we have very nice members. So I am the team leader, and this is Sho Sonoda. He's a full-time postdoc. And this is Achi Nitanda. He's a visiting researcher, and he's now in Kyushu Institute of Technology. And this is Kenta Ono. He was a former PhD student in my laboratory, and he will be a visiting researcher of our team. And he's also working in preferred networks. And we have many collaborators that cannot be listed in this slide. And also we have accepted many intern students, and we have collaborated with them. And we also have a graduate student in the University of Tokyo, and we are working with them. And moreover, unfortunately, we have some industrial collaborators. For example, so we are collaborating with Toshiba through the AIP Toshiba collaborations. So this is a very nice opportunity for us because we are very much theoretical guys, but we have some opportunity to have a collaboration with some application side. Okay. Oh, sorry. Okay. Okay, so from now on, we want to present our contributions to the communities. Okay, the deep learning theory can be roughly divided into three parts. Okay, the first part is the representation ability. So in this analysis, we analyze how accurately the deep neural network can approximate some specific target function. This is something like a function approximation analysis. The second one is a generalization ability. So to train in practice, we needed to train or estimate deep neural network using finite sample size. We don't have an infinite number of observations. So there are some gap between the expected loss and the training loss. So we need to evaluate the difference between training and expected loss. So this is about the generalization ability. The third one is optimizations. It is very known that optimization of a neural network is highly non-convex. So it is non-trivial that gradient descent or stochastic gradient descent can find a good solutions. For each of these topics, so we have contributed like this. So due to the time limitations, we cannot show all of them. So we pick up some of them and present to you. So this is a seminar lineup of today's seminar. Okay. First, I will give a presentation about the overview of our recent advances of our deep learning theory researches. And the second one will be given by Atsushi Nitanda. So here we talk about optimization of a neural network, especially the overparameterized neural network. So this is very much related to neural tangent kernel and mean field analysis. And the third one will be given by Kenta Ono. So here we talk about the oversmoothing of a graph neural network. Graph neural network is one of the hottest topic of deep learning now. So, okay, the final one will be given by Sho Sonoda. He's a specialist of integral representation of a neural network. So he will talk about the functional analysis methods for neural network theory. Okay, so then let's move on to the more technical contents. So in my presentation, I will talk three topics. Each of which corresponds to the one of these three problems: representation ability and generalization ability and optimization. The first topic is much related to representation ability and a little bit related to generalization ability. Okay, so in this part, I will talk about the superiority of deep learning compared with shallow methods such as the kernel method. Okay, so in terms of representation ability, the kernel method is already a universal approximator. That means that if you use a Gaussian kernel, so then the kernel model can approximate any continuous function with any precision. So in terms of representability, so kernel method is sufficient. But in practice, we usually use deep learning, and the deep learning outperforms kernel method. So why is it? So the kernel method can be seen as a two-layer neural network where the first layer's parameters are fixed, and we only train the second layer's parameters. So this is a completely linear model. Okay, but on the other hand, the deep neural network can train all of them. So, all parameters in any layers. So this difference makes a huge gap. Okay? So we want to reveal what kind of difference appears. So to analyze that, so we consider non-parametric regression problem. So this is a very much classic non-parametric regression problem. The output yi is given by f naught xi plus gzi, where xi is distributed on d-dimensional unit cube, and f naught is a true function, and gzi is some observation noise. So we want to estimate this true function from n observations, xi, yi from I equal 1 to n. Okay, so this is a very classic non-parametric regression problem. So suppose that we have an estimator f hat. So this is, for example, the deep learning or kernel method. So then we want to measure its performance. So as a performance measure, we employ the estimation, the mean squared error defined by like this. So this is a square of the L2 distance between f hat and the true function. We take its expectation with respect to the sample observations. If this mean squared error is small, so then that estimator is good. So we compare this performance measure between the deep neural network, the deep learning, and kernel method. Okay, so in the past 2 or 3 years, it has been shown that the kernel method can be outperformed by deep learning depending on the shape of the target function, the true function. So for example, if the true function is a piecewise smooth function, so then the deep can be better than kernel method. And another example is like that. If the true function is included in so-called Besov space, so then the deep learning achieves better estimation error than the kernel method. Another example is that if the data is distributed in some low-dimensional structure, so then the deep can be better than the kernel method. So today, I will briefly explain these two settings. So these two settings are kind of typical situations, okay? And as for the first settings, if we assume the true function is included in the Bessel space, so I will not explain much more details about the Bessel space. So anyways, there is some function class. Then we assume the true function is included in that function class. In that case, so then the true function can have some smooth part and a non-smooth part. So it is not uniformly smooth. So there could be some non-smooth part. So there could be some discontinuous point. Okay, so it is not necessarily continuous. There could be some discontinuous point. So, but this kind of function is a little bit difficult to estimate. If the true function is uniformly smooth, so very smooth, then it is easy to estimate. So in this case, the deep learning can outperform kernel method. Okay, so suppose that we are using a Gaussian kernel for the kernel method. So then it corresponds to something like this. Okay, so we are putting a Gaussian kernel in a regular grid. And because in the kernel method, we fix the kernel function. So then the width of the Gaussian kernel is fixed. So they share the same width. And the width of the Gaussian kernel does not depend on the input x, input location x. So therefore, in the kernel method, we are using the same resolution to approximate the target functions. But the target function has a different frequency or different smoothness depending on the locations. So it is expected that it is better to change the resolution of the basis function depending on the locations. Okay, so here is very smooth. So maybe the Gaussian width can be larger than other places. But here is not so smooth. So it could be better that we shrink. It could be better to use a smaller width to approximate the target function. Okay. But we can show that, so roughly speaking, we can show that a neural network can do such a selection of the resolution. Okay, so the neural network behaves as if it constructs a basis function that have a different resolution depending on the location. Okay, for example, the target function has a high frequency component around here. So then the neural network puts more higher frequency or high resolution basis function around here. And the target function is very smooth around here. So then the neural network will put lower resolution basis function around here. Okay, through the internal layers, it can change the resolution depending on the locations. So this can be seen as a kind of adaptivity. Okay, so based on the target functions, it can change the resolution. So because of this adaptivity, then we can show the deep learning can outperform the kernel method. Another typical example is like this. The target function depends only a few directions, but toward other directions, the target function is constant. In this case, the kernel function can be outperformed by the deep learning. This is because the kernel function cannot find which direction is informative, and which direction is non-informative. But a neural network can find the important direction and it neglects non-informative direction. So then it can avoid the curse of dimensionality. But the kernel method suffers from the curse of dimensionality. So here's a more quantitative evaluation of estimation error. Okay. So as I said, deep learning behaves like it constructs the basis functions adaptively. So it can realize. So then it can realize efficient learnings. Okay. So on the other hand, the shallow method, such as the kernel method, cannot do something like that. Okay. So suppose that the target function is included in the Bessel space. So then the estimation error by deep learning can be bounded by like this. Here, n is the sample size. And so as n goes to infinity, so then the estimation error goes to 0. So we are evaluating how fast the estimation error goes to 0. Okay, so here is S. So S is a kind of a average smoothness of the target function. So S times differentiable. The target function is roughly S times differentiable. And D is dimensionality over the input. So this is known as the minimax optimal rate. So we cannot improve this convergence rate. But if you use a kernel-rich regression, which can be written by this, or more generally, if we use a linear estimator, so then it suffers from the suboptimal rate. So the rate of the convergence becomes like this. You see that this is an additional term. So inside of this term, you see there is a quantity P. So this quantity P represents the uniformity of the smoothness of the target function. So if there is something like a bump shape, so something like this, so then P becomes smooth, P becomes small. If the target function is not uniformly smooth, then P becomes small. So then this term can be larger than this one, and so then this term is non-negligible. Then the convergence rate becomes slow. So this is because the kernel method uses a kind of uniform resolution to approximate the target function. But the deep learning uses something like an adaptive resolution to approximate the target function. Then it is more efficient to approximate the function. Okay. So here's another examples. Okay, so maybe the true function depends on the few directions of the data, but the true function is not dependent. The true function is constant towards some directions. Okay, so in this case, the deep learning can find informative direction, and then it can avoid the curse of dimensionality. But the kernel method cannot find such an important direction. Then it suffers from the curse of dimensionality. Okay. So I have explained some spatial inhomogeneity of smoothness and low dimensionality of the data. But this kind of a property can be extended to more general case. Okay, so that is a function with a property that is destroyed by convex combination is harder to estimate by a linear estimators. So we can show this kind of thing. More formally, we can show this equality. Okay. So let F be the class of the functions that in which the true function is included. The true function F naught is included in this function class. So we calculate the worst case error of the kernel method among the function class F. So the worst case error is same as worst case error of the linear estimator is the same as that of the convex hull of the target function class. We can show like this. So then if the target function class is highly non-convex, there is a huge gap between the original function class and its convex hull. So then this becomes kind of a redundancy. So then the linear estimator suffers from suboptimal rate. Okay, so I will answer your question at the end of the talk. Okay, so thank you for your questions. Okay, and so more intuitively, the linear estimator should prepare a kind of redundant basis functions to cover the whole range of the convex hull of the target function class. So then it leads to the suboptimal convergence rate. Okay. So this non-convexity or convexity argument can explain the many existing researches. Okay, so these examples can be covered by our convexity argument. So then this kind of a unifying approach is useful to explain why the deep can be better than the kernel method in some situations. Okay, so then now let's moving on the next topic, the generalization error of parameters network. So this is more about the generalization ability of a neural network. Okay, the overparameterization. We are considering the overparameterized neural network. Okay, so it is experimentally known that even if we consider very wide neural network, the neural network, the deep learning does not overfit. Okay, so this is one experimental result. The horizontal axis is the number of parameters, and the vertical axis is the test error. So sorry. Vertical axis is the error of the training error or test error. So if you increase the number of parameters, so then the training error and the test error will decrease. For example, the training error will achieve to 0 error around here. And if you increase the number of parameters over this, so then the training error is remaining 0. But from the classical viewpoint, so it is expected that the test error will increase after this one, because if you increase the number of parameters too much, so then maybe the running system will overfit to the data, so then it doesn't generalize. So then the test error will increase here. But in reality, we usually observe that the test error still decrease. So this is a kind of a counterintuitive. So this is one of the big issues of deep learning theories. Okay, so the overparameterization, the generalization performance in the overparameter setting is one of the big issues of deep learning theories. In other words, the number of parameters does not explain the generalization ability. So we need some more refined analysis. Okay, in overparametered settings, the number of parameters can be larger than the data size. Okay, but in experiment, the deep learning can avoid the overfitting. So why is it? One hypothesis, there are many hypotheses. The one hypothesis is that the intrinsic dimensionality, the essential dimensionality of the model is smaller than the data size. So then the deep neural network, the huge model can predict accurately. Okay. So the next question is, what is the intrinsic dimensionality and how large is the intrinsic dimensionality? To tackle these questions, to answer to these questions, we have developed a so-called compression-based bound. Okay, so the intuition behind this bound is something like this. So suppose that we have very huge neural networks, but in many cases, this huge neural network can be compressed to a smaller network. That means without so much performance deteriorations, we can alter this huge network by a smaller network. Okay? So this means that the essential dimensionality, essential number of parameters of this network is much smaller than the actual number of parameters. Okay. So then if we count the number of parameters of the smaller, the compressed network, so then it could be the intrinsic dimensionality. So this explains why the overparameterized network can generalize. And moreover, from the practical point of view, so this is beneficial because by compressing the huge network to a smaller network, we can reduce the computational resources. Okay, so actually we have developed some compression-based bounds like this. These are theoretical papers, and based on the theories, we have developed a new pruning method called spectral pruning, and we have applied this new method to domain adaptation and transfer learning. So yeah, we could combine the theory and applications through the compression-based bound. So here I want to explain a little bit. Okay, okay. So I should explain a little bit. How could this be used for NAS? Yeah, so this can be also applied to NAS. But in NAS, we needed to explore the structure of the neural network. But in our analysis, we are just considering the compressing network. So we are not considering about the exploration of the structure. But essentially, we can consider the NAS. So actually, through some collaboration with application guys, we are looking for such a directions. Yeah, thank you very much. Okay, so then next, I want to explain something about the compression-based bound. Okay, so in our bound, we look at the eigenvalues of the covariance matrix in the internal layers. Okay, in the internal layers, so for some layers, for example, in the else layers, there are many outputs to the else layers. We compute the covariance between these outputs. Then we compute the eigenvalues of the covariance matrix. Then typically we observe that the eigenvalue decays rapidly. So if we sort the eigenvalues in a decreasing order, so then it decreases very rapidly. So this means that the covariance matrix is near low rank. That means the nodes are very redundant. So many nodes are correlated to each other. So then we can discard many nodes. So in addition to that, we also look at the singular values of the weight matrix in each layer. Okay, so if we compute the singular values of the weight matrix, we usually observe the rapid decay again. Okay, so so if the trained network behave like this, so then we can show that that network can be compressed to a smaller network. Then so the next question is how large that the compressed network is. Okay, so roughly speaking, that dimensionality can be given by like this. Okay, so we set some threshold, so theoretically derived threshold. So then we count the number of eigenvalues larger than this threshold. So this is the intrinsic dimensionality. You see that it's very small. But actually, if we compute the intrinsic dimensionality in the real network, so it is much smaller than the original, the network size of the original network. And based on this observations, we have developed some compression-based bound. So okay, so this is the one of them. Okay, so suppose that the J's largest singular value of the weight matrix in the Lth layer is bounded by J2 minus alpha, and moreover, the J's largest eigenvalue of the covariance matrix is bounded by J2 minus beta. So in this case, so we can show the generation gap. So this is the expected loss, and this is the training loss. The gap between the expected loss and the generation, training loss can be bounded by like this. So this is a kind of an artifact, so we can neglect this. So the main term is coming here. So inside the main term, so you see that here is the sum of the ML, where ML is the width of the Lth layer. So this is just a sum of the width of the Lth layer, and moreover, this is powered by like this. So this is smaller than 1. So this is a sublinear order with respect to the width of the network. So here we compare this bound with classical BC dimension bound. In the BC dimension bound, that is like a square root of the number of parameters divided by sample size n. So here ML is a width. So here is the quadratic term, quadratic order of the width. But this is sublinear to the width. So this is much smaller than the BC dimension bound. So in that sense, our bound can partially explain why the deep learning, the overparameterized network can generalize in practice. Okay, so we also have developed some practical method that can be used for pruning, and we have experimentally confirmed that our method can be almost state-of-the-art method. But I skipped some details. And the next topic is the double descent. Okay, double descent is also a very interesting topic in the deep learning theories. So this part is coming from our paper. So this is our paper. Okay, so what is deep double descent? So in this graph, we are plotting the expected loss or test loss against the complexity of the model. This is something like a number of parameters. Okay, in a classical machine learning text, we are taught about the bias and the variance trade-off. Okay, if you increase the complexity of the model, so then the bias will decrease, but the variance will increase. So then we need to balance the bias and the variance. So here is the best one. To find this, for example, we use AIC or MDL or BIC. Okay, so this is a classical regime. But what happens if you increase the complexity of model above the sample size n? Okay, then it is observed that the predictive accuracy or test accuracy again decrease. Okay, like this. So this is called the double descent. This is a little bit strange, but it happens. Okay, so this is a classical bias and variance trade-off, and if in the overparameterized settings, then the test error decrease again. Okay, so we consider this regime. We consider this overparameterized regime. In this overparameterized regime, so we analyze very simple linear regression problem. Okay, so this is a very simple problem. Yi is given by xi transpose beta star plus some observation noise. The beta star is a true coefficient. We want to estimate this from the data. Okay, so in this regime, so we solve this problem. So the beta, the solution beta should satisfy this interpolation equality. So that means for all observations xi, yi, so yi is xi transpose beta. So this is something like overfittings. We completely fit the model to the data. So this is a kind of overfittings. But So the solution or the solution that satisfies this equality is not unique. So we minimize the norm of beta among that set, among the feasible set. So as for the norm of the beta, we employ this norm. So there is a positive definite matrix P that characterizes the norm. Okay. If P is identity, usually people use identity so as a P. So then this is just a Euclid norm, but we consider more general settings. Okay, so this corresponds to the solution of the preconditioned gradient descent. So okay, so that is given by like this. If P is identity, that is a gradient descent. Then T goes to infinity. So then it converges to this solution. We consider more general settings than the gradient descent, where we consider a more general preconditional P. So for example, we may consider P equals sigma x inverse, where sigma x is a population covariance matrix of X. So this is called a population version of a natural gradient descent. This is called the natural gradient descent. So our question is, how does the preconditional P affect the predictive accuracy? So how this metric affects the performance? So that is our questions. To answer these questions, so we have derived a kind of exact form of the asymptotic risk of the predictive accuracy, the estimation mean squared error, when the dimensionality D and the sample size N goes to infinity, and the ratio between D and N converges to some parameter gamma. We assume the gamma is greater than 1, so the over-parameterized settings. Actually, the mean squared error can be divided into bias and variance terms. So we have evaluated some exact asymptotic form of the bias and the variance. Through that evaluations, so we have roughly observed these two notions. Okay, the first one is about variance. So the variance is minimized by the natural gradient descent. So we can show that. Okay, if P is sigma x inverse, so then the variance is minimized among all preconditionals. Okay, so if you use natural gradient descent, so then this variance term can be minimized. But what happens for the bias terms? So unfortunately there is no free lunch. So the optimal P to minimize the bias term is not known a priori. So that can depending on the target function beta star. The true coefficient beta star. To analyze the bias term, so we consider a kind of Bayesian settings. So we assume that the true parameter beta star is a random variable, and its covariance matrix is sigma beta star. And we take the expectation of the test error with respect to the random realization of beta star. We minimize such a Bayes risk. We look at such a Bayes risk. In that case, we can show that the gradient descent generalizes better than natural gradient descent when the sigma beta star, the covariance of the beta star is identity. But on the other hand, if the covariance of the beta star is a sigma x inverse, so that is an inverse of the covariance of the sigma x, so then natural gradient descent is better. So this can be seen as like a misaligned case. Okay, so beta star, the input direction, so the true signal is in a small eigenvalue direction of the sigma x. So the distribution x and the distribution of the beta is mismatched. So in this difficult settings, the natural gradient descent is better. So the intuition behind that is that natural gradient descent amplify the small eigenvalue direction of sigma x. So then we can estimate beta star more efficiently than the gradient descent. So combining these two notions, we can say that the interpolation of gradient descent and natural gradient descent is beneficial to minimize or to achieve better predictive accuracies. For example, we can consider additive interpolation, or we may consider some geometric interpolations. And actually, from theories, from experiments, we can also confirm that the interpolation makes the predictive risk smaller than gradient descent or natural gradient descent. Okay, so this is like an over-parameterization. So finally, I will briefly explain the optimization. Okay, so I will quickly go through the optimization. Okay, so let us consider the training loss minimization in a neural network model. So here, FW is a neural network, and W is a parameter of the neural network. So that parameter could be the infinite dimensional. So maybe you can consider infinite with this two-layer neural network, and you may consider the deep neural network. So anyway, we want to fit a neural network to the data. And for example, you can employ the squared loss, something like this. But just minimizing the loss function could lead to the overfitting. So we add some regularization term. So we employ this very specific regularization. This is just by theoretical reasons, but we employ this regularization. But this optimization problem is the infinite dimensional non-convex optimization problem. This is very hard to solve, but we want to solve this because the deep learning requires this kind of optimization. So to do so, we use a kind of a noisy gradient descent. So if we use just a usual gradient descent, maybe the solution can be stuck around this in the local optimal. To get out of the local optimal, we add some noise, noisy perturbation. So then it can get out of the local optimal, then it can find global optimal. Okay, so the noisy gradient descent is given by like this. This is a very simple form. So basically, this is a gradient descent. So at the case step iterations, WK is updated to WK plus 1. And the update is given by minus the step size times the gradient of the loss function. But so this is just a gradient descent, but we add some Gaussian noise as a perturbations. Here, beta is so-called inverse temperature parameter that controls the strength of the noise. More precisely, we need to consider semi-implicit Euler scheme, but you just consider this noisy gradient descent. Okay, so the interesting point of this gradient noisy gradient descent is that the continuous time dynamics WT weakly converges to the invariant measure pi infinity. That means the WT, the distribution of pi WT converges to pi infinity. Okay, the invariant measure, the station distribution is given by exponential of minus beta times the objective function. So this can be seen as a kind of Bates posterior because this term corresponds to the likelihood. This part corresponds to the prior distribution. So the invariant measure is something like a posterior distribution with Gaussian priors. Okay, so this viewpoint is very useful to analyze the generalization error of the solution. Actually, we can show that the distribution of the case step solution converges to the station distribution in this rate. But I skip some details. So importantly, this convergence rate or convergence bound is independent of the dimensionality. So this is valid also for infinite dimensional parameters. So yeah, we can show the convergence in the infinite dimensional settings. So okay, so finally, so we apply this Ranjama dynamics, the noisy gradient descent, to train the two-layer neural networks. So this can be, we can consider more general settings, but just for simplicity, we consider two-layer neural network. We train the first layer's parameter and the second layer's parameter, and the sigma is some activation function, non-linear activation functions. We assume that the true function and the teacher model, so true function is also included in this model, and our student model is also written by this model. Okay. So then if you apply the noisy gradient descent, so then the solution after sufficient number of updates achieves this estimation error, n2 minus something like that. And also the estimation, the worst case error of the linear estimator or kernel method can be lower bounded by like this. But this is a bit general setting. So let us consider some special settings. So then in some settings, under some assumptions, we can show the estimation, we can show the bound for the estimation error like this. Okay. As for deep learning, the convergence rate of the estimation error is given by like this. So gamma, what is gamma? So gamma controls something like a complexity of the model. If gamma is large, so then the model is more simpler. Okay, so it is a more easier case. So if gamma is large, so this convergence rate approaches to 1/n. But on the other hand, as long as you are using kernel method, so independent of the kernel, so for any kernel functions, So the convergence rate is lower bounded by like this. In the rate of the convergence, you see that there appears a dimensionality D. So it suffers from the curse of dimensionality. So actually, if D is very large, so this convergence rate is similar to 1 over square root n. So there are the square root n times gaps. This is a huge gap. This is a huge gap. So this is because in the kernel method, we fix the first layer's parameters. So then it cannot find the important directions. But on the other hand, in the deep learnings, it also trains the first layer's parameters. So then it can find important directions. So it has some adaptivity. So this research connects the optimization, the noisy grand descent, and the adaptivity of deep learning. So we have shown some gap in terms of the expected loss. Okay, so this is a summary. So we are developing a deep learning theories. We hope that deep learning theory makes the deep learning white box, and it can make the deep learning more controllable. Okay, so yeah, so to say honestly, so we are not so much a high level point, but we are aiming to reach this kind of purpose. Okay. And also, we hope that so the deep learning theory would reveal the essence of the good learning system. So we want to go beyond the deep learning. So thank you very much. So now I want to finish my talk. So, but I want to answer some questions from you. Okay. In some applications, such signal source separation, the optimal dimensionality is very important. There are deep learning approaches to estimate the optimal dimensionality. So I'm not sure what is the dimensionality you are talking about. Okay, sorry, but sorry, I don't understand what is the dimensionality you are talking about. But I think the dimensionality is about increasing dimensionality, maybe. So yeah, so we can define the optimal kind of a dimensionality. So it can be coming from the decaying rate of the eigenvalues or singular values of the covariance matrix or weight matrix. And okay, so another question is that is there any method to distill a huge network efficiently? Yeah. So maybe this is more like a practical things. So there is many methods for distillation, and also there is a theoretical convergence bound or generalization error bound that is using distillations. Yeah. So so that kind of paper was given by Metas Tergalski. So please Google him. So how can we compute the covariance matrix for each layer? It would be nice if you could explain. We just use a training data. We use a training data, so then we just compute the covariance matrix. The characteristics is given just by the empirical covariance matrix. The next question is, what kind of high-level tasks are you evaluating on? Segmentation or object detection or just ImageNet classifications? So this is about maybe the compression-based bound. Yeah. So okay. So what what I was concerning is like any any learning task, but we assume the loss function is bounded, and loss function is one if it's continuous. So then our generalization error bound can be applied to our generalization error bound can be applied to that problem. So therefore, it can be applied to classification or segmentation and any problem. There are many low-rank applications for model compression. So how this theoretical study can be used as a guidance for model compression studies? Well, yeah, you're right. Well, yeah, so maybe you are considering the Taka decomposition or tensor decompositions, maybe. So yeah, this in addition to the singular value decomposition, there are many decompositions, and we have developed some theories for tensor decompositions. So yeah, please look at our website. So we have published one paper about that. Okay. So Okay, so thank you very much. So due to the time limitation, so I cannot answer all of your questions. So I want to finish the question and answer session here. So I want to move to the next session. So I'm sorry. Then, okay, so the next talk will be given by Atsushi Nitanda. So please prepare.
Thank you for introduction. So my name is Atsushi Nitanda. This April, I moved to the Kyushu Institute of Technology, Kyushu Kogyo Daigaku in Japanese. So this university is located at Fukuoka, which is a very nice place to visit. So it would be nice if you have an opportunity to visit. Okay, so I will be talking about optimization for two-layer neural networks with quantitative and global convergence analysis. Okay, in this talk, we present recent advances on optimization for overparameterized two-layer neural networks. The presentation consists of two parts in which we consider different settings of neural networks. One is the neural tangent kernel, and the other is the mean field regimes. In the first part, I present our result and the neural tangent kernel regimes. That is, I show the optimality of average SGD for neural networks using NTK scaling in terms of generalization. And so this work received an outstanding paper award at this ICDEA 2021. So we are very honored to receive such amazing award. Thanks to collaborator Taiji. So next, in the second part, we propose a new method for optimizing neural networks with mean field scaling and provide a convergence rate analysis. So this talk is based on these two papers. So for the detail, please look at these papers. So the problem we consider is the expected risk or empirical risk minimization taking this form. Here L is the loss function, which is typically set to the square loss and the logistic loss. So hypothesis function is a two-layer neural networks taking this form. M is the number of neurons. AR and BR are parameters for output and input layers. And alpha M is a scaling factor depending on the network with M. And it is known that the optimization dynamics crucially depends on the choice of this scale. Theta represents a collection of all parameters. So as you may know, the optimization of the neural networks becomes a non-convex optimization problems, which is generally difficult to solve. So to solve the problem, we typically use the gradient-based optimization method. Clearly, gradient-based method converges to a stationary point where gradient of the objective vanishes. In this sense, convex problem is preferable because the stationary points are global minima. On the other hand, gradient descent can get stuck at a bad local minima because of the presence of many stationary points. So fundamental question in the context is what are conditions under which the global convergence and generalization are guaranteed. One promising idea is mapping the optimization dynamics into function space and exploit the convexity of the loss function with respect to the function. Indeed, the loss is actually non-convex with respect to parameter theta, but it is convex with respect to a function as seen in this inequality. So here, G is the first argument of the loss. So this derivative is taken in the output of the function G. This is a reason why it's better to consider dynamics in the function space. Moreover, generalization bound can be also obtained by characterizing the solution in this function space. For this purpose of mapping optimization dynamics into function space, recently proposed neural tangent kernel and mean field regimes are very useful. So when taking scaling factor alpha m as 1 over m, then the network falls into the mean field regimes. And when taking scaling factor 1 over square root of m, a network falls into the mean field regime. So in these regimes, the training dynamics can be mapped into the probability space and the reproducing kernel field space, respectively. So this is outline of the first part. We here focus on the NTK regime and consider a regression problem with the scale loss function, and we present a convergence rate analysis of average SGD for overparameterized neural networks and the NTK regimes. The key assumption is the specification of the complexity of the target and hypothesis spaces. And such assumption, under such assumptions, we derive an optimal convergence rate of the generalization bound on iterates achieved by ASGD. So theta t is iterates of ASGD, and 0 is the base rule that is the optimal function over all measurable function. And R and beta are parameters used to describe the assumptions. In these settings, the number of iterations t corresponds to the number of examples used to obtain this hypothesis. So this equation provides a rate of generalization bound. And I note that this rate is always faster than 1 over square root t, which is a well-known rate of generalization bound. So the problem setting is here. So we consider the expected risk minimization problem with the square loss functions and consider these two-layer neural networks with NTK scaling. So alpha m is set to 1 over square root n. Here, I briefly review the neural attachment kernel and explain its usefulness. Consider empirical risk minimization problem and run gradient descent to solve this problem with learning rate eta. So this is a step of gradient descent. So next, we take the second order Taylor expansion of the loss function and substitute this gradient update into this equation. Then we get this inequality with small learning rate. So we see that unless theta t is a stationary point, gradient descent decreases the objective by this gradient norm. It is easily derived. So to measure the gradient norm, NTK is very useful. Neural tangent kernel is a type of kernel depending on the parameter of neural networks, which is defined by the inner product of derivative of G, like this. Let the capital K theta be the Gram matrix on n training example xi, xj, and V theta be a functional gradient defined on these examples. Here, functional gradient is a bunch of derivatives of the loss function with respect to the output of G at each training examples. So then this gradient norm is measured as a norm of functional gradient using the Gram matrix K theta. So NTK is very useful in measuring this quantity. That is, so if the Gram matrix of NTK is positive, then the gradient norm is lower bounded by this quantity. And this lower bound does not vanish at non-optimal function G theta. For instance, in the case of square loss, this lower bound becomes the product of the minimum eigenvalue of the Gram matrix and the objective values. So, and combining with a previous inequality, we get an exponential decrease of the loss function like this. So this inequality suggests the exponential decrease of the loss function if this minimum eigenvalue is strictly larger than 0. So this means that as long as NTK is positive, gradient descent converges to the optimal global minimum at exponential rate. In fact, several studies show that overparameterization makes the Gram matrix strictly positive during the training and shows a global convergence at exponential rate for regression problem using the square loss function. Moreover, since the overparameterization localized training dynamics, we can obtain a generalization bound via the Rademacher complexity analysis. Here is the generalization bound obtained in the previous study. In this theorem, gradient descent is performed for t iterations, and for sufficiently large t, and this bound on the expected risk with the squared loss was obtained. Here, y1 to n is a vector of teacher labels, and h infinity inverse is the limit of the Gram matrix K at initial point. The limit is taken with respect to the number of network with n. The second term of this equality converges to 0 as the number of example goes to infinity, clearly. So in order to show the convergence of the entire right-hand side, we consider the convergence of the first term, this term. In other words, to derive a convergence rate from this bound, we should consider the rate of the numerator YH inverse weight Y with respect to the number of examples N. However, unfortunately, the Gram matrix H will degenerate in general as N goes to infinity, which means the slower convergence rate of this term. Indeed, such degeneration is observed theoretically and empirically. This figure depicts the eigenvalues of the Gram matrix of NTK on 10,000 training examples, and we observed a quick decay of eigenvalues in this figure. So here is an intuition on how to derive a reasonable convergence rate. If the vector y lies in the eigenspaces of H infinity with large eigenvalues, then this term y H inverse y takes a smaller value, yielding a good convergence rate. So there is a possibility to derive a convergence rate as long as the target function is well specified using NTK. In other words, we should specify eigenspaces that mainly contain the target function to obtain a convergence rate. In summary, so our question is, can we obtain a better convergence rate with appropriate assumption on the target and hypothesis functions to make this term small? And we answer this question positively. So brief overview of our contribution. So we aim to minimize the expected square loss as explained. And this problem is equivalent to approximating the Bayes rule, which is a minimizer over all measurable functions. To do so, we run single pass averaged SGD, ASGD, in which a fresh sample is observed and used to compute a stochastic gradient at each iteration. As for the detail of the algorithm, we omit in this presentation for simplicity. So for ASGD, we obtain the convergence rate like this, which is always faster than 1 over square root t with the overparameterization. Here t is the number of examples. So this equation provides a rate of generalization bound. So next, I explain the assumption. To do so, we provide some notations and introduce integral operator of NTK. So K infinity is an NTK with infinite width two-layer neural networks. This kernel is a multiple kernel consisting of the sum of two kernels corresponding to the NTK of output and NTK to input layer. So this indicates the multiple kernel learning aspects of learning two-layer neural networks. Next, we define the integral operator on L2 space weighted by the marginal distribution on X. So this is a distribution on data space X. So the definition is here. This operator can be considered as a limit of Gram matrix of NTK with respect to the number of example N's appeared in previous NTK theory on empirical risk minimization problem. Moreover, we note that the operator is type of smoothing function of f because the function value of sigma f is a simply weighted sum of f using this kernel function. So this is kind of smoothing operator. Let μi and phi be a pair of eigenvalue and eigenfunction of the integral operator, and μi is sorted in decreasing order. Then the power of the integral operator along basis phi is defined like this. So this power is naturally extended to the L2 space by taking linear expansion of this. In general, eigenfunctions of small eigenvalues correspond to the high frequency of the functions. Hence, high frequency relatively vanished by the power of integral operator if this value of R is large. In other words, the image of power of the operator is composed of smooth functions with respect to the NTK, and R controls the smoothness of the function contained in this image. And then RKHS associated with NTK is represented as the image of the square root of sigma like this. From this, first decay of eigenvalues of phi means smaller RKHS, this because this condition is getting stronger when the decreasing speed of eigenvalue is fast. So here is main assumption in our theory. The first is the smoothness of zero. So zero is the base rule. And this condition says that the base rule exists in the image of this operator with R. So this assumption controls the smoothness of the base rule as explained. And the second one determines the decay speed of eigenvalues. So this controls the size of RKGS associated with NTK. So this is a more formal version of the main theorem. Under appropriate assumptions, we obtain the convergence rate on the expected risk as achieved by ASGD. A major difference from the informal version is appearance of this term epsilon. Epsilon is a gap between learning dynamics of neural network and its projection onto RKGS. This epsilon can tend to 0 as m goes to infinity. In addition to this, the maximum number of t we can take also depends on the value of network width m. So hence, this theorem says that this convergence rate can be achieved if the number of neuron m is sufficiently large to ignore this term epsilon. So I again remark that this theorem provides the rate of generalization bound because this number of iteration t corresponds to the number of samples obtains these hypothesis functions. Moreover, this rate is known to be the minimax optimal in this learning problem settings. Okay. So we empirically verify the usefulness of the specification of target function by comparing single layer and two-layer learning. However, we omit the detail because of the time limitation. So, however, we empirically observe the usefulness of the specification of the target function using the NTK, which is consistent with our theory. So, as for the detail, please look at our paper. Okay. So next, let's move to the second part. So I quickly explain the second part. We here consider the neural networks with mean field scaling and propose a new method for optimizing the mean field neural networks. We remark that the difficulty of deriving convergence rate for mean field regime is well known in the context. Hence, additional assumption or regularization probably required to conduct a reasonable convergence rate analysis. In this study, so we consider the KL regularized empirical risk minimization problem and give a polynomial convergence rate guarantee. I'd like to emphasize that this is the first study that provides a convergence rate analysis under this problem setting. Okay. We here consider an empirical risk minimization with a general smooth loss function, such as square loss and logistic loss. And hypothesis function is two-layer neural networks, and taking this form as in the first part. But the difference is the scaling factor. So we here consider the mean field scaling 1/m. This is a diagram to explain the idea behind the proposed method. We here denote by theta r a pair of parameters AR and BR. And we assume that theta r follows a distribution Q theta D theta. And we denote by H theta r x a component AR sigma BR x of the network for simplicity. So here, this is a two-layer neural networks under mean field regimes. And this converges to the integral of H theta x by using the density function Q theta, because each parameter theta r follows the density function Q. So this is simply infinite width neural networks. Next, let's consider corresponding empirical risk minimization problems for these hypothesis functions. On one hand, for the finite width networks, the problem is actually non-convex with respect to the parameter theta because of the non-linearity of the loss function. On the other hand, for the infinite width network, the problem is convex with respect to the density function Q, because this density acts linearly for HQ. So this diagram indicates the usefulness of considering the optimization performed in the probability space of Q. So there are already many studies based on this idea. These papers study the convergence property for mean field regimes. Then they consider different settings each other, but all studies agree the difficulty of the convergence rate analysis in the discrete time settings. In other words, convergence rate analysis is non-trivial and probably require additional assumption or regularization. So in this study, we consider the KL regularized empirical risk minimization problem of this form. Here, the first term is the expectation with respect. Here, the first is empirical loss, and the last two terms are regularization, which correspond to the Kullback-Leiber divergence to the zero mean Gaussian. It is clearly observed. Notation EQ is expectation with respect to the theta which follows the density function Q. So this regularization guarantees the generalization. Indeed, we derive the generalization bound for the solution of the problem. For the detail, please look at the paper. However, the main focus in this study is the optimization for this problem. The variable of the optimization problem is the density function Q. Hence, this problem is the functional minimization problem on the probability space. For this problem, we derive a new method which exploits the convexity of the loss function with respect to the density Q. Okay. So Ranjama algorithm is very relevant to our method. So here briefly review the Ranjama algorithm. Let f be a potential function on RP which corresponds to the space of theta in our settings. Then for the function f, Ranjama algorithm performs a noisy gradient descent using Gaussian noise like this. Then it is known that the random variable theta k converges to the Gibbs distribution taking this form regarding k divergence up to a certain error or eta error. So eta is the step size. In other words, Ranjama algorithm can minimize the entropic regularized linear functional with respect to the density Q. So the problem is this. So Ranjama dynamics can solve these problems because the minimizer of the problem corresponds to the Gibbs distribution taking this form. So the Ranjama algorithm can be used to solve a certain class of the optimization over the probability space. However, Ranjama algorithm cannot be applied to our problem settings because the problem we want to solve is not linear functional, but nonlinear functional with entropic regularization taking this form. So the problem Ranjama dynamics can solve is this, but the problem we consider is this optimization problem. So the difference is the nonlinearity with the density function of this term. So to overcome this limitation, the basic idea is to generalize Ranjama algorithm to double loop scheme. More specifically, we first linearize the nonlinear part of the objective at the current iteration Q and construct a subproblem using the linear approximations. Since the minimizer of subproblem is a Gibbs distribution because of the linearization, so we run Ranjama algorithm to solve the subproblems in the inner loop. Intuitively, the minimizer of these subproblems converges to the optimal distribution by analogy with the finite dimensional optimization, and this intuition is correct. So this figure depicts the image of the method. In the outer loop, dark colored Gibbs distribution, which is a minimizer of the subproblem, converges to the optimal solution for the original problem. And this update for the Gibbs distribution can be achieved by Ranjama algorithm. So this is an outline of the proposed method called the dual averaging method. In this step, we calculate the linearization of the nonlinear part. And in the next, so very noisy outside of my room, sorry. And in the next step, we run Ranjama algorithm to solve a sub-problem derived by linear approximation and approximately solve the sub-problem and obtain Gibbs distribution. Approximation to the Gibbs distribution. As explained, this distribution converges to the optimal one. In fact, for this method, we provide a sample complexity to achieve an epsilon accurate solution of the K-regularized empirical risks in this scenario. So although we skip the detail, but I'd like to emphasize that this is the first result that shows a polynomial convergence guarantee for this problem in discrete time setting. Okay. So since dual averaging is an ideal method, we should derive an approximation of the method. Fortunately, we can approximate the method in a very simple way. Recall that dual averaging method updates the distribution in the outer loop and these updates can be achieved by Ranjama algorithms. So we can empirically approximate these updates by running Ranjama algorithm with multiple particles. And this approximation is the approximation of dual averaging method. And we call this approximation scheme particle dual averaging. So we here compare two algorithms, dual averaging and particle dual averagings. On one hand, dual averaging updates the density function Q, and this update implies an update of infinite width networks like this. On the other hand, particle dual average method updates the empirical distribution, which is a bunch of particles, theta R, and this update implies an update of finite width network like this. So we can say that PDA is a method for optimizing the two-layer neural networks under mean field regimes. So moreover, the convergence guarantee for PDA is also valid via the result for dual averaging, because PDA converges to the DA when we take a sufficiently large number of particles to approximate these updates. Okay, so this is the summary of our method. So finally, we empirically observe the convergence of PDA method on synthetic datasets. For binary classification problems, we used the double circle dataset, and the red and blue points represent positive and negative examples. And these curves represent the evolution of the particles initialized around the center. So we observe each particle evolve to classify the dataset well. So particles evolve from the center to the edge on the circle to classify this double circle dataset. For regression problems, we compare PDA and SGD for mean field scaling and SGD for NTK scaling. First, we observed the superiority of mean field scaling over NTK scaling under specific problem settings. So this setting is rather artificial to perform the superiority of the mean field regimes. And moreover, we observed the usefulness of KL regularization on the comparison of PDA and SGD, where SGD does not utilize KL regularization in the problem. So PDA can outperform SGD because of the effect of KL divergence in this experiment. Okay. So here is the summary. So in the part one, I briefly review the NTK theory and explain that the specification of the target function with NTK is useful to derive a convergence rate of the generalization bounds. Based on this intuition, we derive an optimal convergence rate for ASGD. In addition, we empirically observe the importance of the specification in experiments, although we skip the detail. So in the part two, we introduce a new method for optimizing neural networks with mean field scaling. it is well known to conduct, so the difficulty of the convergence rate analysis for this setting is well known. So the additional assumption or the regularization will be required for the reasonable convergence rate analysis. So in this study, we consider KL regularized empirical risk over the probability space and provide the first quantitative convergence rate analysis for this problem. So finally, we would like to remark that there are several pros and cons between NTK and mean field regimes. So unified analysis of these two regimes may be very important direction in the future work. So I finished the presentation. Thank you for listening.
Hey, thank you very much. So we can take one or two questions. Okay, so we have already one question. Okay, so the question is, so okay, so I will read. So for the NTK work, what is the requirement for neural network over parameterizations? How large comparing to the sample size?
Okay, so in our theory, so the number of neurons required in our theory depends on the number of iterations t exponentially. So this dependence is not so good because it means a very huge overparameterization is required. But I'd like to emphasize that the main purpose of this study is to derive optimal convergence rate for SGD. So reducing the network width is not the main objective in this study. But yeah, I agree that the reducing the network size, overparameterization size is very important on research directions. Yeah. And however, it is somewhat difficult, but it is very good if you have we have a nice idea to overcome this limitation. Yeah.
Okay. So do you have any questions? Any other questions? No? Okay, so then thank you very much. So let's move on to the next speaker. Okay, the next talk will be given by Kenta Ono. He will talk about the oversmoothing of graph neural network. So please start.
Thank you for giving me opportunity to have a talk about my my work. I'm Kenta Ono from Preferred Networks, Japan. I'm going to talk about the oversmoothing of graph neural networks. And this presentation is based on my PhD work at the University of Tokyo. So first, let me introduce myself briefly. I'm an engineer at the company, and in parallel, I was a PhD student at the University of Tokyo, and my supervisor was Suzuki Sensei. And as a PhD student, I studied deep learning model that have structures in their architectures. For example, like convolution neural networks or graph neural networks. In this presentation, I'm going to give a talk about the theoretical analysis of graph neural networks. And this is the contents of the presentation. So first, I briefly introduce what graph neural networks are, and I'm going to give two topics. One is oversmoothing of nonlinear GNNs, and the second one is the analysis of multi-scale graph neural networks, which I will explain later in detail. So graphs are ubiquitous data representation, which represents the relationship between nodes or objects. This is a very ubiquitous from a small graph like molecules to gigantic graphs like social networks or user item graphs that is used for the recommender systems. And we want to apply machine learning methodology to such a structured data. And graph neural networks is a deep learning model dedicated to such kind of structured data sets. There's no unified definition of GNNs because there are very many graph neural network variants. graph neural networks basically gives a representation of the components of graphs, such as nodes or edges, or graph itself, using the graph structures and the node features and edge features. And we can pass the representations to the downstream models, which do not assume the graph structures, such as SVM or multi-layer perceptron or another graph neural networks. So we can think of graph neural networks as an interface for that connects the graph data and general machine learning models. The GCN, which is full name is Graph Convolution Neural Network, is the simplest and the most popular graph neural network variants to date. One layer of graph neural network, GCN, can be formulated as follows. Throughout this presentation, I denote the number of nodes. We assume a big graph and consider the task of predicting the property of nodes in the graph. And we denote the number of nodes in the graph by n, and the dimensionality of feature vector associated with each node by C, capital C. One layer of GCN consists of two operations. One is node aggregations, where each node aggregates the representation from neighboring nodes and do some operations using these operations. For example, taking sum of these representations or average, take the mean of the representations. Another operation is a nonlinear transformation common to all nodes. And this operation is typically nonlinear, such as in the case of GCN, this is a linear transformation followed by element-wise nonlinearity, but we can generalize it to multi-layer perceptron. Well, and GNNs has been successful in many applications area. For example, several studies have shown that GNN is useful for, simulating the physical many particle systems or predicting the side effects of drugs, or we can use graph neural networks for object recognition. So I believe that GNN is a promising approach for structured graph data. However, I'm sorry, it's a bit corrupted. However, from theoretical point of view and practical point of view, GNNs have a big problem known as oversmoothing. Specifically, it is empirically known that deep nonlinear GNNs often do not perform well when we stack many layers. Left figure shows the prediction accuracy. We apply graph neural networks to predict the node properties. And the x-axis is the number of layers of the GCNN, and the y-axis is the prediction accuracy. And please take a look at the dashed line. As you see, when we stack more than 5 layers, then the prediction accuracy decreases rapidly. That means to achieve our better performance, we cannot stack many layers. This is in contrast to the classical deep learning model such as multi-layer perceptron or convolution neural networks, where we can stack more than 100 layers. The first part of this talk is why this happened and how to prevent this phenomena. And as you see in this presentation, we can attribute this phenomena to the oversmoothing and that is the side effect of the node aggregations in the graph neural networks architecture. Previous studies have shown that theoretically analyze the oversmoothing phenomena for the linear GNNs where the activation function is the identity matrix, identity function. In our study, we have shown that oversmoothing also happens on nonlinear GNNs. And it is natural to ask how to overcome or mitigate oversmoothing. There are several ways to do that, but we focus on multi-scale GNNs, which is the central topic of the second part of this presentation. So as we shall see in the first part of this talk, plain GNNs may suffer from oversmoothing. And this is problematic because it may reduce, it may be harmful for the expressive power of graph neural networks and may cause underfitting of the model. The idea of multi-scale GNN is to introduce the subgraph information at various scales to predict the property of the center node. Since node aggregations increase the receptive field, that is the subgraph, the radius of the subgraph that we are focusing on by 1, we can increase the radius of the receptive field by 1. So one simplest way to realize this idea is to use the skip connections, and that connect the intermediate output of the single scale GNN to the final output, and the intermediate output sum them up. And there are several studies for the analysis of multi-scale GNNs. We are one of them. And we use the boosting theory to analyze the multi-scale GNNs and derived the optimization and generalization guarantees for the multi-scale GNNs. This is the overview of this talk, and I go on to the first part of this talk. Let me first formulate the problem setting. We are interested in the node prediction task. That is, we want to make a prediction on each node in the graph. So the data set is the pair of the feature vector X and the label Y, where we consider the binary prediction task. And the first M data points is training sample, and the remaining N minus M data points are test sample. And for the node prediction task, it is standard to formulate it as a transactive learning, where during the training phase, we can use the feature level pairs of training sample and feature vector of the test sample. And the goal is to predict to give a prediction to every node in the graph. So the differently from the supervised learning setting, we can see the feature vectors of the test samples, the test sample. We consider the slight extension of GCN that I explained earlier, where one layer nonlinear transformation is replaced with the multi-layer perceptron. So one layer of GCN can be formulated as follows. And here, A tilde is a variant of adjacency matrix of graph of the underlying graph. Specifically, it is the normalized adjacency matrix of the graph augmented with self loops. So I corresponds to the self loops. And for the nonlinearity sigma, we consider our element-wise ReLU function, which takes the maximum of the zero in an element-wise manner. So let me formalize the oversmoothing of graph neural networks. And to do that, we introduced the subspace M in the space of the collection of representations, that is R to the power of n times C. I will define it mathematically in the next slide. And we think oversmoothing as the convergence to the M, which is measured by the distance to the subspace M. We denote it by dm. And we have shown that the distance distance of the output of the else layer FL is upper bounded by the distance of the input representations X. Here, lambda represents the spectral gap of graph Laplacian. Now, that corresponds to the effect of the multiplication of the adjacency matrix. And SL is the weight singular value. That is the effect of the application of nonlinear transformation, and that is MLP. This is the definition of the information-less representation as the space of information-less representation M. Here D is a degree vector plus all one vector, and so we define M as the D to the power of 1/2 times R to the power of C. The important property of the space M is that if the collection of nodal representation X is in this subspace, then suppose two nodes have the same degree. Sorry, I should have said that we assume that underlying graph G is connected for simplicity. Then suppose two nodes have the same degree, then corresponding representations Xi and Xj are identical. Intuitively, that means the X only has the information for we cannot distinguish the node I and the node J using the information of node degree. Because node degrees are identical, then their node representations are same. In that sense, M consists of the representations that are informationless for node prediction tasks. And for the node connected graphs, we additionally require that nodes I and J are in the same connected component. Here we briefly overview the proof of the theorem to see what's going on underneath. If it were not for nonlinearity, it is a simple linear algebra. We see that multiplication of the adjacency matrix converges to the constant times degree vector. And for the effect of nonlinearity, we can prove that application of nonlinearity do not increase, strictly increase the distance to the informationless space M. Here we use key facts of the property of ReLU. We use the combination of the two facts. One is that degree vector is non-negative, and ReLU is the projection onto this cone. So as you see in this figure, ReLU effectively decrease the distance to the invariant space. We can see it geometrically in the low dimensional space, low dimensional case. Here are some consequences. First, the distance to the invariant space, informationless space M is lambda times S to the power of L, where L is the number of layers and S is the supreme of the singular values. In particular, when the singular value is strictly smaller than the inverse of lambda, then we see that the node representations goes to the informationless space M exponentially. And in addition, the convergence rate is characterized by lambda, which is determined by the topology of the underlying graph G. And as you see, nonlinearity just decreases the distance to the informationless space. That means if we use the same proof, if we apply same proofs to the linear GCNs, we can obtain the same upper bound of the distance. And finally, lambda inverse is the threshold of that determines whether a GCN is this GCN deems to the oversmoothing or not. So if the threshold is very large, then we see that most GCNs suffer from oversmoothing. And from the spectral graph theory, we see that large and dense Erdős-Rényi graphs are large dense Erdős-Rényi graphs applies with high probability. And here is some experiments. We apply GCN to the node prediction task. And in this case, the threshold lambda inverse. Okay, we apply graph neuron GCN to the node prediction task. And in this experiment, we normalize the weight singular value S to a constant value at every training iteration. And the constants are 0.5, 1.05, which is slightly smaller than the threshold, and 3.0, 10.0, which are far larger than the threshold. And as you see, when the singular value is smaller than the threshold, the prediction accuracy decreases. It's worse than the baseline. In contrast, when the singular value is well larger than the threshold, we see that the prediction we can improve the prediction accuracy of the graph neural networks. So we see that lambda inverse is a good criteria for the prediction performance of the graph neural networks. And here is some related works. We use the distance to the invariant space M as a matrix of oversmoothing, and we considered the nonlinearity. There's another study for theoretically analyze the oversmoothing of nonlinear GNNs. They introduced the Dirichlet energy, which is quadratic function of X, and which is 0 on the informationless space M. And they considered nonlinearity, leaky ReLU nonlinearity as an activation functions. And there are several countermeasures for oversmoothing. And what is important point here is that we can interpret this methods from the viewpoint of the information-less space M and threshold lambda inverse. And for the large-scale GNNs, we will talk about it in the next part of this talk. And let me skip this point. So the summary of the first part is that the issue was that deep nonlinear GNNs suffer from oversmoothing. And in this study, we characterize the oversmoothing as the distance to the information-less invariant space. And we showed that little GCNs are as vulnerable as linear GCN to oversmoothing. And this is first part of this talk. And let's move on to the second part of this talk. Okay. So as I explained earlier, we are interested in the large-scale GNNs as a countermeasure for oversmoothing. Let me first formalize the problem setting mathematically. We again consider the node prediction task in this part. However, we want to analyze the generalization ability of the graph neural networks. So we introduce the randomness of the training and the evaluation procedure by shuffling the data points, especially indices of data points uniformly randomly, and take the first M data points as a training sample and the remaining N minus M data points as test sample. And again, we consider a transactive setting, and the task is a binary classification task. And the figure in the right-hand side is the schematic view of the large-scale GNN we consider in this part. Horizontal arrows represent the node aggregations, that is multiplication of the adjacency matrix from left. And vertical arrows represent the multi-layer perceptron common to all nodes. And we add the intermediate output. We sum them up, the intermediate outputs, to give the final prediction. And our idea is to decompose the multi-scale GNNs into the single-scale GNNs and consider it as the ensemble of single-scale GNNs. That is, each weak runner is a single-scale GNN. By using this interpretation, we can incorporate the boosting theory to the analysis of large-scale GNN, and we can derive the optimization and generalization guarantees. And from the practical point of view, boosting GNN is beneficial because we can use constant memory usage with respect to the number of weak learners, T here. This is much efficient than much more efficient than usual large-scale GNNs, which is trained by a backpropagation. And here is the optimization error bound. We assume that each weak learner satisfies the weak learning condition, WLC in short. I will explain it later. Then we can bound the training error loss as follows. Here, M is the training data sample size. Training sample size, and gamma T is determined by the parameter of the weak learning condition. Weak learning condition intuitively represents the condition that each weak learner is close to the gradient, negative gradient of the training loss. And alpha T and beta T determines how close which weak learner is. In particular, gamma t is the lower bound of the squared cosine of weak learner and negative gradient. So the larger gamma t is, the closer weak learner is to the negative gradient. And in particular, if gamma t is independent of t, we can derive that the training error rate is inverse of the big number of weak learners. Here we refer to the relation to the oversmoothing. As we saw in the first part of this talk, singles GNN is oversmoothed when we when t goes to infinity. However, this theorem implies that as long as weak learners are expressive enough to satisfy the weak learning condition, then the ensemble, that is multi-scale graph neural networks, has guaranteed to have the training upper bound. So we can guarantee the prediction, optimization guarantees for multi-scale GNN under the weak learning condition. And using this optimization guarantee, we can derive the test error bounds. It's a bit complicated, but the essential part is that the upper bound consists of the optimization error that is monotonically decreasing with respect to the number of weak learners, and the model complexity term, which is upper bound, which has the upper bound independent of t when the adjacency matrix, the operator norm of the adjacency matrix is small. So, so that means if the operator norm of the adjacency matrix is sufficiently small, the upper bound of the test error is monotonically decreasing with respect to the number of weak learners t. And we can experimentally see that this is true empirically. Here is the training and test accuracy, training and test loss with respect to the number of weak learners. And as you see, as long as weak learning condition is satisfied with some parameters, training and test loss keep decreasing. And that is aligned with the theory. And let me skip here. So the part two, as a summary of the second part of this talk, we consider the issue of this part was that GNN suffer from oversmoothing, even if we introduce a nonlinearity, as we saw in the first part of this talk. And the contribution of this study is that we give an interpretation of multi-scale GNN as the ensemble of single-scale GNNs. And using this interpretation, we derived optimization and generalization error bands of multi-scale GNNs. And we have demonstrated that empirical behavior of GNNs align with the theory derived from the boosting theory. So the conclusion, we have seen that current GNNs suffer from the oversmoothing, and we formulate mathematically an oversmoothing and gave some conditions for the oversmoothing for nonlinear GNNs. And in the second part, we analyzed the multi-scale GNNs, and we derived optimization and generalization bounds using boosting interpretation. Since the time is over, so let me finish. This is the end of my talk. Thank you for listening.
Okay, so thanks. So because we don't have so much time, but I can take one question. So in case of anomaly detection, which type of GNN is expected to perform better? In case of anomaly detection, which type of GNN is expected to perform better?
Well, to the best of my knowledge, I do not know any application of GNN to anomaly detection. However, since so if we can construct a graph for homophily graph, then I think any standard GNNs can apply and perform well. Here, homophily means that neighboring nodes tend to have similar properties. Because node aggregation operations implicitly assume the homophily of graphs. So I think the problem is rather not. I think the important point is with the type of graph neural networks, rather how to construct the graphs suitable for GNNs.
Okay, so are there any questions? So, okay, so let's finish this talk. So thank you very much. So then the next talk will be given by Shon Sonoda. So this is the last talk. So he will talk about the functional analysis methods for neural network study. So please start.
Okay. Hi, everyone. Thank you for attending. I'm Sho. I'm a researcher in deep learning theory team, postdoc researcher. So let's begin. So this is my self-introduction. I'm Sho, and I'm now a postdoc researcher at RIKEN. And before joining RIKEN AIP, I was in Waseda University, and I earned my PhD degree in 2017. And my major is machine learning, and recently I'm concentrated on neural network theory based on harmonic analysis or differential equation or probabilistic numerics. And I also have some experience in machine learning application for EEG data or steel making or autonomous driving, or this is I just began very recently, but quantum machine learning. Oops. So let me start from a big question. What is the typical solution of deep learning? So this is an illustration of deep neural network that recognize the image. Well, we input the image from left side, then the neurons start processing information and finally spits out the probability value. For example, this is a camel with 90% or this is a rock with 80%. So definitely this network acquires some function for processing information, but we do not know what function is acquired because the deep learning process is black box. So suppose you're a machine learning engineer or data scientist to design network. Maybe you want to know what solution is typically acquired because in order to avoid a malfunction or improving the performance of deep neural network. And those demands is resulting to ask which is a typical solution. But the characterization of deep learning solution is very difficult. So for a theoretical study, this is typically formulated as a regularized empirical risk minimization problem, like equation 1. Here, G is symbolized as a network, deep network, parameterized by theta, and theta is restricted to some capital theta and regularized by some omega. So this problem is difficult because this deep neural network is nonlinear, and which makes that optimization problem non-convex. So we need to break down the problem. And in this slide, I will review some recent progress in deep learning theory. One is about global convergence. So despite nonlinearity, the deep learning is known to achieve the global convergence. And recently, very recently, it has been shown to achieve zero training error theoretically. So there are two main streams. One is mean field theory, and the other is lazy learning. I have to emphasize here that they are essentially a shallow model. And the other topic is that about the implicit regularization. So deep learning is set to impose implicit regularization. And this is not clearly revealed what it is. But very recently, Shizat and Woodworth proved that when the scale of initial parameters are very small, then the implicit regularization by gradient descent is equivalent to L2 norm regularization. So these facts somewhat support us to estimate, consider the regularized empirical risk minimization program for theoretical study. Okay, and in this talk, I will talk about first, I will introduce integral representation and rigid transform. And second, this is the main part of this talk about the characterization of shallow solutions. This is not deep, but the shallow solution. And it will be also presented in the AI stats in next week. And if I have a time, I will also review some more recent results. Okay, so here I will explain the definition of integral representation. In the upper section, this illustrates an ordinary finite neural network, finite shallow neural network that have activation function sigma and AI, BI, CI, their parameters. And the parameter dimension is limited to fixed to D. And I have to point out here that this formulation is equivalent to the typical, very typical element-wise formulation of shallow neural network. And in the lower section, this is the integral representation. And in the integral representation, all possible hidden parameters A and B are integrated. So we do not need to take care about which AI and BI to use before training. And instead, the only parameter what we have to estimate is gamma AB. In the finite model, this was originally output parameter CI. So CI is the indices by number I, but in the integral representation, all A and B becomes have the same role as the index. So the output parameter gamma becomes a function in some function space. And one advantage of this formulation is, as Nitanda-san or Suzuki-sensei also mentioned, that in the continuous setup, the continuous network is linear in this new parameter gamma. So this is one advantage. Okay. And here I list some pros and cons of integral representation. I already mentioned about this first and the second part, and thirdly, this is there exists a density result. I mean, the finite continuous models can be easily approximated by finite models. So this motivates us to use analyze continuous model instead of analyzing finite model. And most importantly, we have a closed form inverse operator for this integral representation S of gamma. And this is known as a rigid transform, and this will be the main topic today. So I will explain it later. And of course, there are some disadvantages of integer representation. One is, of course, because the parameter is infinite dimensional stuff, so we need to use a function analysis, and this is basically difficult. But I have to emphasize that this surely helps geometric understanding of deep neural networks. And the second disadvantage is that in particular for rigid transform R, the feature map sigma AX minus B is limited. So if we want to extend these results to another structure such as a convolution or deep structure, the extension is not trivial. But again, I have to emphasize that there are some new results, new extensions to convolution structure or deep structures are emerging. Okay. And maybe I need to skip this slide. This is just about general result by the finite approximation. So this rate is known as Baron's bound, and here I list the very general result by Kukova. And it covers not limited to neural network, but it also covers, for example, the Fourier transform. And so this is about a very general set of continuous model. Okay, let's introduce the rigid transform. So here I suppose that the activation function to be a temporal distribution. This is a very large class of functions that includes ReLU or hyperbolic tangent. And in addition to sigma, we introduce another function rho, and I suppose this to be very smooth. And essentially, we can choose this rho independent of sigma. And by using sigma rho and data generating function f, we define the rigid transform as in the equation 4. So this is essentially the inner product of fx and some feature map. And when the sigma and rho satisfy the admissibility condition, this is a sort of a coupling condition. And this looks a little complicated, but essentially, this is a weighted inner product of sigma and rho. And the admissibility condition demands us that this weighted inner product is not orthogonal nor diverge. And when sigma and rho satisfies this AC, then we have that for any L1 function f, if we substitute rigid transform with continuous neural network, then it reproduces the original data generating function f. And here the inner product is just a number, so we can rescale it to 1. Then this equation is exactly equal to fx. But as we can also see that if this inner product is 0, then it degenerates to 0. So neural network fails to reconstruct the original function. Fine. So I think many of you are not familiar with rigid spectrum. So I give one visualization of rigid transform. For the sake of visualization, I assume that the input dimension x is one-dimensional. Then the rigid spectrum will be two-dimensional signal because A has the same dimension with x and B has one dimension. And for this kind of artificial data, we can compute the rigid transform by using numerical integration, and then we can visualize it in the AP space. And here I assume the sigma to be a hyperbolic tangent and rho for admissible rho to be a Hilbert transform of the second derivative of Gaussian. I do not explain why this is admissible to sigma, but we can easily check by directly computing the admissibility condition. So in the spectrum, we can see 5 red arms. This is a positive arms and 5 negative arms. And as I mentioned, that there are infinitely many different admissible functions because admissible condition is just in a product. So there are infinitely many admissible functions and non-admissible functions. And in the case when the rho is admissible, then if we substitute this Dirichlet spectrum to a continuous neural network, the continuous network reproduces the original function. I know you can see some deviation from the original data, but this is just my implementation on numerical integration was poor. And so this is an admissible case. And another interesting thing is that the non-admissible case, if we substitute the non-admissible case to our continuous neural network, then it spits out the zero function. So what this means? This means that we clearly see some non-trivial pattern in the parameter space, but if we substitute the neural network, then it outputs a zero function. So this means that this is the null component or null element in the parameter space of a neural network. So this is, I think, very specific to a neural network and very different from another shallow models such as the kernel methods or Bayesian networks. And I recently deeply analyzed this null structure and mostly completely characterize the structure of null space. Okay, so this is just a side information. Okay, interesting. And so some of you may wonder that how null elements can affect in the real space, because this is just the null elements. Yeah, it's reasonable. But one way is that despite the S of R of F equals 0, because rho k is not admissible, if it is in the course of a finite approximation, this is not completely null. So we can see some effect of the null components. So take for example, a simple Monte Carlo integration of zero network. So of course, it eventually converges to 0 as the hidden unit number tends to infinity. But in particular, when the hidden unit number is small for two different non-admissible functions, the behavior of loss is different. I think this reflects the difference in the shape in the parameter space. Interesting, right? Okay. So to this point, I explained the fundamental property of integral representation and Dirichlet transform. And they are independent of the minimizer of deep learning training. And from now, I will explain the characterization of shallow solutions. Okay, first I will begin with explaining interesting simulation result. We consider training a finite neural network that has D core 10 hidden units with the same data set as I used before. And I use SGD with weight decay for training. And plot the ABC points in the AB space. Because the network has 10 hidden units, after the training, we will have 10 points in the AB space. And sure, you cannot see any reasonable pattern in the AB space, but if we increase the number of network, because SGD training is non-convex optimization program, if we change the initial parameter, then they converge to different points. So if we have two networks, each network have 10 hidden units. So after convergence in AB space, we will have 20 points. And let's increase the number of network. If we have 5 networks, then we will have 50 hidden parameters. And 100, 500, 1,000, 5,000, 10,000 hidden parameters. So after repeatedly training as many as 1,000 network, then obviously there are non-trivial frequency in the AB space. So, and we can again find the 5 red arms and the blue five blue arms. And here they are green box, but they have almost a 0 value. So this is just a remaining residue of initial parameters. I used uniform distribution for initialization. And yeah, this is very similar to the rigid spectrum. This is very interesting, but to this moment, this is just an empirical observation. And our latest contribution is that mathematically rigorously proves that the left side weakly converges to the right side if we increase the parameter number d and the sample size n. Okay, shall we explain our main results? So main result is composed of threefold. First, for technical reason, we restrict the parameter space in the compact domain. So for A, this is just the interval, and for B, we assume the torus structure. So this results into assume that the activation function becomes periodic. And then I'm of course sure that ReLU or hyperrectangent is not a periodic function, but so this is just a technical demand. And we can, so in practice, we can take this period T as large as needed. So in practice, we cannot distinguish if the activation function is really periodic or non-periodic. And but anyway, we changed the parameter space. So we first verify the reconstruction formula still holds. And in addition, it satisfies the Planck-Schurter formula. Then the first result is in the idealized setup. We consider optimization space or optimization program for the continuous model. And we also assume that all the information of data generating function F is given, and also impose the L2 regularization term. Then, by the strong convexity, there uniquely exists a minimizer, and can be proved that the minimizer is equivalent to the rigid transform. Here, 2 points. One is that if we substitute this rigid transform to a continuous neural network, then it reproduces FP over beta plus P. So this is essentially a shrink estimator. And this is a natural consequence of imposing L2 regularization term here. And secondly, as I mentioned, that the rigid transform can be defined with almost any rigid function rho. But if we consider this minimization problem, we can prove that the rho is equivalent to sigma. So there are no redundancy after the convergence. I think this is a very strong result. And finally, we consider a finite setup. I mean, the network is as finite as d term, and the sample size is also as finite as n. So we assume the empirical risk minimization program with the L2 regularization term again. And then mathematically rigorously prove that if we take the limit of the model size d tend to infinity and the sample size n tend to infinity, then it again converges to the rigid spectrum. So this essentially explains the previous interesting resemblance of, for example, right? Okay, perfect. Very interesting, right? Oh, oops. And we also clarify that the convergence is in the weak sense for D and in probability because we use law of large number in the Banach space. Okay. Finally, I will review some more results. So last year, due to COVID, I was working home, so I can concentrate it on the very harmonic analysis part of neural network and specify the complete structure of neural space. And yes, I also succeeded to extend the rigid transform on some topological groups. So this is, I think, this is a very strong results. And already I have another application. I derived lower bounds, approximation lower bounds for some network. And I'm also working on deep theory, continuously deep network. And last year I derived a Barron's bound for continuous deep network. So I do not step into the detail of these topics, but so please stay tuned. In particular, I'm preparing these reprints. So this is one application of Richard's analysis for approximation lower bounds. So this is very tight. And if you are interested in this result, in the preprint, I have clarified the rates for some limited function class. And I think we can use this result for designing networks. And this is more conceptual slide. And as I said, I'm also working on continuous deep neural network. And this is, how to say, the fundamental thoughts. So if, say, the continuous width is about point gamma in a function space, then the continuous depth should be about the curve gamma t in the function space. And as we have seen, the strength of continuous width is the linearity of parameter. I mean, this is the so the integral representation theory or overparameterization theory is something about reparameterization of shallow neural network. And important probably is the linearity of parameters. And plus, of course, the rigid transform. So what is the linearization of depth? I think one promising approach is that the neural ODE, because it parameterize neural ODEs, parameterize this curve by a vector field, and a vector field is a linear stop. So I think this is very promising. And I'm surely this attracts attention recently, but I'm also sure that many problems left unsolved. It's just the introduction of a recent Barron's bound for deep neural network, but it's essentially the same. Here comes the number of units, and this is the L2 loss, and this is a different Barron's bound. Okay, so let me conclude the talk. So the big question, we start from characterizing deep solutions. And in this talk, I mainly talk about the shallow structure. And now the characterization of shallow structure, shallow solutions are characterized by rigid transform, as long as it achieves the empirical risk minimum. And in addition, I explained some fundamental property of integral representation, and what is important is linearization. So I think that if we want to succeed in deep learning study, what we need, but not yet established, is a linear theory of depth. Okay, so this is the end of my talk. Thank you for listening. If you have any question, I will pick up.
Okay, so there is already one question. Okay.
Yes.
So I guess you can see, but I read that. This is quite interesting. Can you confirm that my understanding is correct by answering the following questions? The first question is, the continuous integral form has a higher representation capability than traditional neural network?
Well, that's a good point. But so I think the expressive power is the same, because when people say that the expressive power of finite network, it is about the density. So usually they take the infinite limit. And after taking the infinite limit, it converges to a continuous model. So essentially the same. And one result I explain is that, sorry. Yeah, no, this. So this reconstruction formula that the continuous network is universal in L1 function space. But of course, finite network can be also universal in this L1 space. So essentially the same. And the inverse transform corresponds to training the network. Well, that's a good point. So according to this result, if the training process achieves empirical risk minimum, then directly computing this rigid spectrum is equivalent, because we now prove that minimizer is unique. So as long as it achieves the zero training error, then this should be equivalent to the rigid spectrum in some setup. And their training algorithm for multi-layer networks, yeah, it's still developing, but I think recently, for example, the Taiji-san developed the Ranjama dynamics theory. I think this can be combined with this kind of integral representation theory.
Okay, so are there any questions? So you can directly talk. No questions? Yeah, so since the time is over, so maybe the people are very tired. So maybe this is a good time to finish. If you have any questions, so to all the speakers, if you have any questions, so please raise your hand or type your question on the Q&A tab. Okay, so perhaps there is no. Okay, so let's close this seminar. So thank you for coming. So everybody, so thank you for coming. So this seminar was very nice for us, because we could present our recent researches to other guys than the outside of the Riken or University of Tokyo. So then that is our great pleasure. So if you are interested in our researches, so please feel free to contact us. So then I would like to finish this seminar. So thank you very much.